So 22% per year for 20 years means we're going to get the 1 plus the 0.02. We're going to raise that to the 20th power. And we want to know what is that percent, what's that odd that it's going to increase by over that 20-year period. Anybody throw that in your calculator? What did you get?
48.595%.
48.95. Can you give me one more?
595%.
5.995%. Anybody else get confirmation on that? Okay. Is that making sense? Okay. We ready to talk about the next one, or do you need a minute? We're ready? So if we want 150,000 in 30 years, that means we want 150,000, and we don't know how much we want to start with. We're going to get 3% compounded daily, so that's going to be 1 plus 0.03 divided by 365 raised to the 365 times 30. So on the newer calculators where it actually shows that moving up as the exponent, you can now divide this over and enter this into your calculator with just one data entry. If you have an older calculator that doesn't push this up, you're going to need parentheses around this to show the multiplication. So from here, we can take that 150,000 divided by, and then do 1 plus, just like what you see written here is what you're going to type into your calculator. And anybody, we still working on it? You got an answer, Nora? What did you get?
I got 60,987.70.
Is anybody getting that same thing? Sounds like no.
I got 60,987.56.
0.56.
But I tried to use the actual calculator thing the entire time, like that.
I did it all in one equation.
So you did it piece by piece?
Well, yeah, but then I used
Still captured.
selected the yeah, I selected those answers. Maybe the calculator probably rounded still though. I'm guessing.
Yeah, the only way to store those is to press store as X, and then it keeps all of the values, even though it doesn't show you that it does.
Why don't you try it this way now and see if you get the same thing there. I'm imagining you will. Yep. Okay.
Same thing, 0.70.
It's interesting. I didn't know that. Because it carries about a lot of decimal places still when you do that. It surprises me that it would be still off. We ready for this one, or do you need a minute? No response. Yes, you're ready. You can just move your head, or no, you need a minute. Okay, so we're ready. So an investment decreases by 40% in 5 years. What's the annual rate? So we want to know what is that annual rate in 5 years. Now, if it decreases, we start with our P. We don't really know how much that is. If it decreases by 40%, how much do we still have? 60. So then we need to write that as a 0.6p. That make sense? Okay. So then you can divide out your p. So it doesn't really matter how much you started with, it's going to still be the same. Now to solve for the r, we're going to have to raise it to the 1/5 power. And so that's going to go into your calculator. You'll subtract 1, make it into a percent. There you are. Doing some review problems. So anybody ready for the whole
isn't it negative 9.112%?
Yeah, it should be a negative. Negative 9, did you say?
Yeah, 9.712.
712%. Anybody else getting that? Sounds like we get consensus on that one. Okay. So I can see this, let's get some people up at the board to do this one here. Okay, so let's get 4 or 5 people up to the board to do this one, that's where we are. I'll pause the video for a minute. So what we've gotten there is we're going to take the 1 plus, and that's going to be 0.016 to the 12 for a full year, and subtract 1 and make it a percent. And I think what we got was 20.983%. Okay.
So if it says it's compounded monthly, you divide by 12, but if it's monthly interest, it's already in the month.
Right, so if this was an annual interest compounded monthly, then you would make that 0.016 divided by 12.
Okay.
But in this case, this has already been made into a
Yeah.
monthly interest. We're trying to find what the annual rate is.
Okay, thanks.
We don't know that. Okay? Okay. So let's bring different people to the board and try this one. Okay, I'll pause the video here. So on 6%, we're writing that as e to the 0.06. We're going to call that 1 plus r, and I think we're getting 5.8. That doesn't sound right. Is that what we got? Should be bigger than 6, right? 6.184%. I like that better. 184.
Did you do it times a negative?
Yeah, I'm not sure.
Negative?
Yeah, see, that looks like you did you do that as a negative?
Yeah.
Because then this would, then that would be, if this was decreasing by 6%, then this would be the amount that would decrease that as an annual rate.
You solved the wrong problem.
Yep, you made up
It's
your
still
own.
the right answer.
Right answer to the wrong problem. Okay, questions on that one? These still seem to be challenging. Okay, let's try this one. Get another group up here and do this one.
No?
Make sure in your final answer you either say that it's a negative percent or that it's decreasing by that positive percent. Okay, I think we got 5 point. What was it? 5 point. So annual is going to be, so we go 1 minus the 0.05, which is 0.95, and we set that equal to e to the k. And so we're going to take the natural log of that, and that was our negative, what did you say, 5.129?
129.
So negative 5.129%, or decreasing by 5.129%. Okay, last one, you're gonna have to do this one by graphing. Okay, so let's bring a group up, and Gage, you wanna show Ben how to do this one? I'll give them the answer on that. So we just graphed this and found the points of intersection. Questions on that? That working for you? What was the one you wanted to see? There was another one on there.
Number 24, so investment increases by 50% over a decade, by what effective annual rate does it increase?
Okay. So we have an investment's going to increase by 50% over 10 years. And we want the effective annual yield, annual rate. Okay, so in this case, what we want, we don't know the R. And that's our original investment, which we don't know either. We know that was 10 years in the making. And after that 10 years, our original investment grew by 50%. So it's now 1.5p. and then we're going to solve that for the r. You get it from there? Okay. Anything else? Questions on the homework from last couple days? If not, I'm going to talk about a little bit of new stuff, and then hopefully we'll be able to squeeze in some more practice on older logarithm stuff as well. Remember, we're testing on Friday.
Are
So
logs gonna be on the test?
logarithms are not on this test, yet, but we'll get ready for that one shortly there. So we're going to use our properties of logarithms here. So I'm going to review the properties of logarithms and try to kind of come up with some maybe somewhat contrived problems to force you to use those different properties of logarithms. So remember, there's really only three of them. So one is that the logarithm, any base of two things that are being multiplied are what?
Log dot base of x plus log
Good.
base.
So, and we'll do this both ways. So when we take a single logarithm and break it up into multiple logarithms, we're going to call that expanding. And when we take multiple logarithms and make them more compact into a single one, we're going to call that condensing. So expanding is going from left to right, condensing is going from right to left. And in a similar fashion, the logarithm of a division is going to be
Log of x.
good. So we say the difference of the logarithms, and then the one we've been using more regularly is the one that helps us solve those exponential equations. And that's the one that says we can bring that exponent out in front and make it into a multiplication. Okay, so let's see if we can then, I'm going to erase this and give you and ask you to either expand or condense these things. So we're going to first expand, and we're going to have the logarithm. I'll just make it a common logarithm so we don't have to write the base. And we'll say x to the third, y to the fifth over the square root of z. So this is a single logarithm, and we're going to break it apart. We're going to expand it and use all the properties of logarithms that we can bring to bear on this. So I'm going to do this in many steps, but you're welcome to shortcut this and write it, more quickly. So first we can see we've got a division, and our property of logarithms says we're going to get the log of the numerator minus the log of the denominator. So we can call that the log of x to the third, y to the fifth, minus the log of the square root of z. That okay so far? Now we have here a log of a product. So we can make that into the sum of the logs. So we can call this the log of x to the third plus the log of y to the fifth minus, and in the preparation for the next step, we can write the square root of z as the log of z to the 1 over 2 to the 1/2 power. Okay? And then we can now use that third property of logarithms and bring all those exponents out in front. And so we're going to get to 3 log x plus 5 log y minus 1/2 log z. Is that okay? All right. Now that you see how the game is played, yes, actually.
Would you have to make sure that you have parentheses around the addition part so that there's not a, or would it just be written like that?
Like in here? Actually, this is okay as it is, yeah. So the thing we most have to worry about, writing the numbers in front is clear that that's not inside the logarithm. you know, if we were gonna have something, if we wanted to, for some reason, say the log of x times 4, then that's not clear. Do we mean,
Oh, but like around the two terms, like 3 log of x plus 5 log of y, would you have to put parentheses around that to make it clear that that's all?
that's where it came from, or?
No, since
Because
they're
the
both,
order of division, or the order of subtraction and addition doesn't matter.
right.
Right. Yeah, so this is actually okay. I'm gonna give you one in a minute that's, you're gonna have to think about maybe a little more carefully. We'll see, but I don't wanna take all the fun away. So we'll see what we can do with it. I don't know if I answered your question.
You did.
Okay, any other questions? All right, so I don't know whose turn it is to come to the board, but let's do that. We're going to do the natural log of, we'll say x to the 4th over, we've got the cube root of y times the 5th root of z to the 3rd power. Oh my goodness, this will be a fun one. Pause the video for a moment. So we are going to think of this as the natural log of x to the 4th minus the natural log, and I'm going to write that as y to the 1/3, z to the 3/5. So we can call that 4 natural log x, and then this becomes an addition. So we have 1/3 natural log y and 3/5 natural log z. And then finally, we can distribute that negative sign. So at the end of the day, what you see is everything that was in the denominator is being subtracted. So I think that's kind of a nice mental check. At the end, you see both these two terms that were in the denominator that we're dividing, each have a minus sign in front of them. Okay, so now we turn the game around the other way, and we're going to condense. So I'm going to give you one that's all broken apart, and our goal is to condense it into a single logarithm. Okay, so you want to see one done, or do you have the idea? Want to see one done? I'll do one. I'll do an easy one, leave you with a harder one. I'll do one that's kind of hard. So we'll say logarithm base 3 of, we'll say 2 logarithm base 3 of x plus 2/3 logarithm base 3 of y minus 5 logarithm base 3 of z. And so I'll do this in many steps, but you're welcome to shortcut this along the way. So the numbers that are multiplying the logarithms can be brought up into the logarithm as powers. So that will be the logarithm base 3 of x squared. And then we'll get a plus a logarithm base 3 of y to the 2/3. I'm going to come back to that in a moment and write it in radical form. And then a minus logarithm base 3 of z to the 5th. We can see that the addition of logarithms is going to make that a product. So I'm going to make that the log base 3 of x squared, and I'm going to write this in radical form. So the 2/3 power is the cube root of y to the 2nd. And then we have a minus a logarithm base 3 of z to the 5th. And the subtraction becomes a division. So remember, at the end of the day, there's not lots of logarithms, there's only one logarithm. So x squared cube root of y squared over z to the 5th. But that's all inside of one logarithm. So a lot of times I see misconceptions where people will write a log divided by another logarithm. That's not what this means. It's the logarithm of a division. Yeah.
What would you do if they weren't all log-based?
That's a great question.
Two different logs.
That we will talk about later. We would have to do a change of base. And we can do that actually. So a change, since you brought it up, we might as, that's a great question. And this comes up a lot next year because next year we prefer natural logarithms to everything else. So if something is a logarithm other than a natural logarithm, we're going to change it. So if we have a logarithm base A of x and we want to convert it to a logarithm base B of x. So if we had a different base of a logarithm and we wanted to make it like the others, then what we do is we first go to the exponential. So we'll write a to the y equals x. You with me there? And then we'll take the logarithm of the base that we want to change over to. So for us, that would usually be like a common log if we're trying to do something on the calculator, or next year it'll be always natural log because it's just way easier to work with in calculus. But we'll just say it could be anything. So we'll take the logarithm base b of both sides. Because that now allows us to move that y using the property of logarithms out into the front. So that's the logarithm base b of a equals logarithm base b of x. Is that okay? Remember that y was our original logarithm base a of x. We're going to divide that over, so our y is going to be a logarithm new base of x over logarithm new base of the old base. Remember that? That y was our logarithm base a of x. So when you've done a couple of hundred of these, as I have anyway, and I don't know if you'll ever get to that point, but if you want to change it, you just take, if you want to make it a new base, you just make it the base that you want. And then your adjustment factor is you have to divide it by the logarithm new base of the old base. And this, we just did this actually yesterday in calculus, interestingly enough. So in calculus, if we had something like the log of x, we don't like a base 10. So we will convert that to, we just make it a natural log of x over the natural log of the old base. So it's just logarithm of the base that you want of what you had before, and then you divide it by the logarithm of what you want of what you're trying to get rid of. That's called change of base. Because you'd have to get them all to be the same before you could do anything else. Okay, good to go? I think we're ready to come aboard now with that little bit. Let's do, we'll say 2, 3 fourths logarithm base 2 of x minus 7 logarithm base 2 of y minus 1/3 logarithm base 2 of z. We're going to condense that into a single logarithm. You don't know? Well, so the idea is something like this. So I'll do this kind of briefly. So we're going to make that 3/4. We're going to make that logarithm base 2 of y to the 7th. Logarithm base 2 of
Excuse
z.
the interruption. Life Touch is at the west end of the Commons, and at the beginning of second hour, if we can have students with the last name starting with A through K take their photos, that would be great. Once again, at the beginning of second hour, A through K. Thank you.
So if you do this one at a time, we'll make the argument that, and then we'll try to shortcut it after this. So now we have another division. So you could correctly think of this as being divided by that z to the 1/3. Now you got, this is a complex fraction, clearly. So this is a fraction divided by a fraction, which means inside that logarithm, we can multiply by the reciprocal. So it goes to there. So the bottom line, I mean, after you see this once, not too long, hopefully, once or twice, what you see is both of the things that were being subtracted end up in the denominator, because we're dividing by both of those. And then I'm going to go back to the radical notation. So the 3/4 we're going to write as the 4th root of x to the 3rd. And we have our y to the 7th. And then the z to the 1/3 is going to be the cube root of z. So again, one logarithm at the end of the day. And once you've done a few of these, you see that anything that gets subtracted ends up in the denominator.
If you were like, if you changed the, 1/3 log to a z, if you added that instead of subtracting it, would that put it in the numerator? Or
Yes. Yeah, great point. So if hypothetically, this was the question from the beginning, yes, then this would have been in the numerator. Very nice. Okay, got a new game we're gonna play, but again, the real point of it is to use these properties of logarithms. So I'm gonna tell you that we're gonna say the log of 3. So the log of 3 is approximately 0.477. And the log of 2 is approximately 0.301. And that's all we know. We do know it's a logarithm base 10. Oh, am I out of time? Jeez, where does the time go? I'm gonna do one real quick here. So the log of 9, we're gonna try to find that value without using your calculator. It's a mystery. How about log of 3 squared? 9 is 3 squared. So it's going to be 2 log 3. And now we can say, well, that's going to be 0.477 times 2 and get that answer. So you have to decompose those into 2s and 3s, possibly powers of 10. All right.